as I told you, detonation is not easy to initiate. And if you take a reactive medium, a gaseous medium, and in this medium, which is called the temperature in such a way there is no reaction, and you assume that in a small volume, you have you increase the temperature, and you start an explosion there, and at a constant volume almost, because it is very fast. It turns out that you do not ignite detonation by this way, because the pressure that you obtain is too small, and you do not ignite because you need a pressure that is 25 atmospheres, something like that, at ordinary pressure temperature, so that you reach only 10 and it cannot work. Now, it turns out that this is becomes possible if the medium that the reactive medium that you are considering is not uniform. So, for this and the key point of that is the following: that let's say the induction time, which is the time necessary to start the reaction for that. For example, it's not instantaneous. You have a delay. This delay is coming from the chemistry. It turns out that this delay, this induction time, is strongly decreasing when decrease when increasing the temperature, or strongly increase. What I say? So the induction time is strongly decreased when you increase the temperature, and strongly increased when you decrease the temperature. So you see here is a profile of reaction rate. Here it is for an initial temperature of 2000 Kelvin. The other is at 1925, and the dash is 1825. So you see this induction increase strongly with the decreasing the temperature, and the other, or vice versa, the induction decrease when the temperature increases. Now, assume that the pocket, the reactive pocket you are considering, is not at uniform temperature, but you have a, let's say, assume that at one given time you produce a pocket with a gradient of temperature at hot temperature. So this is a difficult problem it's not easy to do that experimentally, but assume that you have such thing. What is going to happen? That everything is non-reactive, no reaction at T equals 0. And suddenly you increase the temperature, but not in the homogeneous way, but like with a gradient. Assume that you can do that. I will explain you how to do that, because this is not easy. In that case, what is going to happen? That the hot slides ignite before the cold side, because the induction time is shorter at the hot temperature than the lower temperature. So you see, you ignite the hot slides before the cold sides. So you are going to have a propagation of induction front. You know where so you are going to have an ignition front propagating because the time ignition time is small, high temperature. Excuse me. Yes, it's small and it's larger, so you start later. here you start faster, here you start later. So you have an induction profile, an induction front, excuse me, propagating. And the speed of this induction front is the inverse of the induction gradient. You see? Now, if this propagation velocity of the induction is equal to the sound speed, what does that mean? What is going to happen? That you are synchronizing the heat release with the pressure rise. You see? And that's make what is called a Rayleigh instability, which is a mechanism of the acoustic instability in engine, for example. This is the same. So as soon as the heat release is in phase with the pressure, you develop an instability. This, I will explain that in the course of tomorrow, maybe today, I don't know, I will see. For the for the acoustic instability of combustion. So the mechanism of spontaneous initiation is, in fact, that the combustion, the pressure pulse propagates with about the speed of sound, and this is a critical, you know, a critical condition for synchronization. And here I have just shown how a simple model to describe the runaway of the pressure. You know, the runaway of the pressure is like grows like the temperature, the time. Excuse me. The amplitude of the pressure pulse increase linearly with time at the rate at the same rate as the reaction rate. In fact, so this excuse me. So this was a basic idea of Zeldovich. This is an ignition of a detonation through a gradient of temperature, initial gradient of temperature. There is developed, not easy to read, but an asymptotic analysis that been developed 20 years ago on this problem. It turns out that we, sometime later, before the analysis of sharp and short and sharp, we show with this, with also Lontin here, that, you know, here is a initial gradient of temperature. This is a profile of the pressure up. So here you see you reach the Chapman-Jouguet pressure, you know, here, which is this is precisely the point at which the ignition front propagates at the same speed as the sound speed. Here it's, so now this is the profile of the pressure, Chapman-Jouguet pressure when you define, when the temperature, the upstream temperature is decreasing. But what we notice, you know, the idea was following. If I have, if I am able to construct a temperature gradient hot, on the hot side, you know, this is okay. Let me see if it is shape. I know. Okay, it is out of the scale. You're right. So what we discover, it is a good collaboration between the theoreticians and Lantinhe, who was an excellent numerician. He did experiments, and you know, he saw this transition here, but sometimes he saw that the detonation fails at lower temperature and cannot be transferred to the uniform state, cold state here. And this phenomena, we have explained this phenomena once again, you know, as a C-shaped curve, expressing, you know, that there is a turning point you have here of this Chapman-Jougues of the detonation in a gradient temperature. So you have a turning point, and once again, this turning point is describing a transition of something, and the transitions tell you that, okay, you ignite at high temperatures as predicted by Zeldovich and John Lee, but later on you may quench the detonation because of the gradient, the same gradient, but at a lower temperature. So I will not explain into detail that simply it's because you have, once again, a turning point. Now, in other words, the CG detonation cannot survive to a strong temperature gradient at low temperature. You ignite, but it could not survive. So this is important if you want to develop, you know, because how can you build this gradient? In fact, you build such a gradient using laser methods. With a laser, you can. It's not so easy to do, but experimentalists know how to do. With a laser, you may strongly increase the temperature in a small region where you focus the laser. And this was done by John Lee, in fact. It was done by John Lee. And so this allows you to build a very high temperature with a gradient, because simply with a gradient, because the intensity of the laser is not uniform. You have an intensity which is maximum in the center of the spot and decrease to zero on the way outside. Therefore, you have a gradient, and this gradient of temperature, because of with the laser, you can do that in a time shorter than the characteristic time of the induction time at the higher temperature. This is the key. So you have the gradient of temperature which is built before any reaction, then the reaction starts, and you have this induction front propagating. And if this velocity of this reaction induction front equals the speed of sound, this is the critical condition, then you ignite the detonation. And now, unfortunately, we prove also, and this was, that's very interesting. We proved that, you know, in '94, and it was this phenomena of quenching was obtained by a group with Misha Lieberman much later. There is only 6 years ago. They proved that also numerically. They do that even with a complex chemistry. So this is, you know, to show you that sometimes simplified analysis can predict phenomena that are observed later on. Because it was observed that you do not ignite, you know, it was observed that in the experiment with a flash of laser flash, sometimes it works, sometimes it doesn't work. Why it doesn't work? Because you ignite the detonation and then the detonation is quenched a few times after it was ignited. And this is the explanation. Okay, this is, if you are interested. Now, let me go to the most interesting part of my lecture, to my opinion. And it is also the most recent part of my analysis. This is the deflagration to detonation transition problem. What is the deflagration to detonation transition? It's an abrupt transition between two opposite regimes of propagation. What does that mean? You know, a flame is a reaction diffusion waves, as I told you, which is markedly subsonic. It's, the speed of the flame is much smaller than the sound speed. Detonation, on the opposite side, is a shock-driven supersonic combustion wave without diffusion beyond the lead shock. There is no diffusion in this problem, except maybe you have to retain, but it is not diffusion, it is dissipation with Boltzmann equation in the lead shock. So you have a problem where the combustion waves propagates. The propagation is subsonic and controlled by the heat diffusion process, and this is strongly subsonic, as markedly subsonic, as I explained to you before. And suddenly, a sudden transition to a supersonic wave. So, what I want to stress also is that when you are thinking about the quasi-steady state propagation regime, there is no other propagation transition in the laminar regime. There is no other transition, no other wave propagating at constant speed than a flame and a detonation. There is nothing in between. And this is really surprising. What is the mechanism which is responsible of this transition? And how this transition is observed experimentally? Let's remind you some experiments. The pioneering experiment of Tony Oppenheim in Berkeley in '65 shown clearly that the detonation may occur in various forms. And, you know, sometimes when you look to a flame propagating in a tube, the transition occurs by hotspot at a point, you know, in the viscous boundary layers. Sometimes the local explosion occurs outside the boundary layer. And indeed, up to now, there is no mechanism of deflagration to detonation transition that is generally agreed upon as being universal. So it looks that there are different mechanisms for this transition. In fact, the situation is not clear at all. Things are well established. What are there? First, the transition is local. It occurs in a very small hotspot like an explosion starting in a very small portion. It's not a global phenomenon, it's a local phenomenon. And it is sudden. That occurs, in 10 minus 6, 10 minus 7 seconds, when you look to the explosion. Very short. And this occurs either inside or outside the boundary layer of the wall. And also it can occur sometimes the boundary layer just in front of the flame, not in the flame, sometimes on the flame. So, but the fact is well established. There is Tony Oppenheim. Tony showed clearly with his co-worker that everything starts at a point. He calls that a hotspot. So this is something which I was fascinated by this problem. And in fact, when I was young, Tony Oppenheim invited me to Berkeley it was in '85, to study this problem from a theoretical point of view. He was asking me to try to help him to understand. I did my best, but at that time, I did not succeed at all. And I said to Tony, okay, Tony, I am not good enough to help you, and I will do other things. Let me finish my flame theories, and maybe sometime I will be back to the detonation problem. And this is one regret of my life, because Tony was a charming man, very, very interesting man. And I love him very much. He was very good. And I would be very happy to try him to explain things. It turns out that he died before much. So I don't know, maybe he died 15 years before, at least 20 years ago, or 50 years ago. So, but it turns out that now, I think I obtained one of the answers. And this is one of my regrets of my life. Oh, I should have done that when he was alive. He would be so happy, he will jump everywhere. Because he was very, he was a man like that, very, very, very. So, okay, this is why I work hard recently, because by myself, because now I am retired, so I work by myself. And in fact, I think I got one answer. Maybe not the only answer, but one answer. What I am going to try to explain to you is what is my belief. I want to see an intrinsic mechanism of laminar flame, because when you look to the literature, there are confusing, especially when you look to the literature in experiments. Every time they said, okay, the transition turbulence is essential. That's wrong. Turbulence is not the essential mechanism. It can help, but it is not the essential mechanism. And I was interested to show that there is a mechanism intrinsic for laminar flames to transit suddenly in a detonation. As I say, turbulence can promote an early transition. That's right. I will explain you why. But it's not it's not an essential ingredient in the transition. And I start working on that recently. Here I have recall there there is one case of transition inside the boundary layer. I will not look at that today because this transition does exist, it is observed, but this is a phenomena which is coupling a local explosion by the spontaneous ignition mechanism of Zeldovich coupled to a compressible wave. It is a little bit complicated, and I did not have a clear idea of the mechanism yet, of this one. So what I am going to do is, I was very inspired by the experiments of Michel Lieberman, let's say 15 years ago, maybe even 14 years ago, where I will focus my attention to a transition when a laminar flame, elongated flame, propagates in a tube, and I will look to the problem when the transition occurs on the leading edge of the flame. It will be an elongated flame, and then on the leading edge of the flame, outside the boundary layer. And this was observed in this experiment here, excuse me. So this for me was very important because it was the first experiment showing a transition in the laminar regime, outside the boundary layer also. So this is clearly one, this motivates me to look at the problem. What are the basic ingredients? Now I have to show you how I developed my understanding. The first basic ingredients, when a flame is ignited close on a closed wall, when the flame, there is what is called the piston effect of the flame. The gas, a column of gas ahead of the, let's say, the flame acts like a semi-permeable piston. Why semi-permeable? It is because the flow velocity just in front of the flame is not is smaller than the flame velocity. You know, a piston, when you have a piston, the flow just on the piston has the same velocity as the piston. In a flame, the flow velocity is non-zero, it's important, but it is smaller than the flame. So it's like a semi-transparent piston, and a part of matter cross the flame. I will explain you that. You know, I will, to begin with, I will just recall, but briefly, what is a wrinkle flame. A wrinkle flame is simply a laminar flame was the shape of which front the front is wrinkled by some turbulence or some instability, whatever it is. But there's, you know, when you look at a scale larger than these wrinkles, you know, you can consider this flame as quasi-planar, okay? And it acts like a semi-permeable piston. Okay, the flow velocity that you have now in front of, because you are wrinkled, the wrinkling factor increases the flow velocity by a factor which is called the wrinkling factor, which is the flame surface area divided by the cross section. You know, if the flame is planar, this folding factor is 1. Higher is the folding factor, higher the flame is the flame velocity, and the flame velocity, which is in that case called the turbulent flame velocity, is simply the laminar flame speed relative to the burnt gas multiplied by the folding factor. And now you see this is a propagation of the semi-permeable piston, and the flow in front of this flame propagate as a velocity equal to the difference in the laminar flame velocity relative in the burn gas minus the laminar flame velocity relative to the fresh mixture. The difference is a ratio, is almost the ratio of the temperature, -1. So here is what is called the piston effect. I put S different from 1 because I am going to use that in my next talk, but to understand it's not necessary to speak about, to consider a wrinkle flame. Just the laminar flame will give you also the planars, will give you also the same provide the same. So what occurs sometimes when you look to the flame propagating that the wrinkle, the flame surface increase, and therefore the flame accelerate because you increase this factor S. And now the third basic ingredient is that the heating of the fresh mixture ahead of the flame by compressible effect. This is another ingredient. You know, if you look to a simple problem of a piston in an inert gas, and if you look to the flow ahead the piston, when the piston accelerates, the temperature increases because of the compression. Because of the compression wave. I will explain that in more detail. So these are some basic ingredients. And the last one, maybe the most important one, is that the flame speed, UB here, is highly sensitive to the temperature. So you see that there is, you see immediately a possible coupling between the wrinkling of the flame and the velocity. Not because only the wrinkling increase, but UB increase. And this is strong with the temperature. So you see the increase, the main increase, okay, if S increase, you increase this, but UB you increase. So these are the main ingredients. This is recalled here, and just for you to well understand, to make you well understanding this piston effect. The piston effect is here, you see, for a planar flame. Okay, the flame velocity propagate at the burn gas laminar, the laminar flame on the burn gas. When you sit in the flame, you enter with a cold mixture at the laminar flame velocity. This is called laminar, and the other relative to the fresh mixture, and this is the velocity, laminar flame velocity relative to the burn gas. And just by change of referential, when the burned gas is at rest here, the flame propagates at the laminar flame speed relative to the burned gas, and the flow is the laminar velocity, laminar flame speed of the piston minus the laminar flame speed relative to the fresh mixture. So here, this is the same picture as before. Now it's clear that if you put in motion a column of gas, you are going to build a shock wave ahead. So the simplest configuration to consider is a situation in which you have a leading shock propagating at velocity d, followed by a flame propagating at a much slower velocity, so that here, this is the slow velocity, so the distance between the flame brush and the shock increase with time. Now, a first mechanism in mind obtained by Schelkin, what is called the Schelkin scenario, is the following. If you increase the wrinkling, you increase the flow velocity. But if you increase the flow velocity, you increase the turbulence, if the flow is turbulent. And so you increase the velocity again. But now you increase the Mach number. If you increase the Mach number, you increase the temperature. But the temperature here is the same as behind the shock, is the same as just in front of the flame. So you increase the temperature. So, okay, forget about what I said just. So you increase the temperature behind the shock, and if the temperature goes over the crossover temperature, you ignite the detonation. So this was the first idea of the transition deflagration mechanism developed in the 40s, 50s by the Russian, well-known Russian scientist, Schelkin. You see, this is completely wrong. Wrong because of the experiments show that this is not the case. The transition never occurs for a Mach number sufficiently high to have a temperature above the crossover temperature. Typically, the transition which is observed in a tube, the Mach number of the shock in front of the flame is no more than 3. But the Mach number of 3 gives you a temperature which is well below the crossover temperature. So there is no way to ignite a detonation this way. The problem should be much more subtle than that. Therefore, let's say that serendipity is not explained, and I hope to have made some progress in that. So I'll back now. I remind you some experiments. There are 2 experiments that are very instructive. The first one is by a Chinese group around 25 years ago, looking for flames in sub-millimeter tube. You know, very small tube, Therefore, the Reynolds number is very low because the radius of the tube is so small. So you are laminar. And when you use a very energetic mixture, you observe detonation in that case, transition. It turns out that the experiment of Lieberman a little bit later was concerning the tube of 3 or 4 centimeter radius, or let's say, because it was rectangular, if I remember well, it's the size is more than 3 or 4 centimeters, so it's a centimeter's tube. Here, and both of these use a very energetic stoichiometric mixture, hydrogen, oxygen, pure oxygen, or acetylene, oxygen, pure acetylene. And the flame temperature is typically about above 3000 K, and the Chapman-Jouguet velocity of such mixture is typically 3000 meters per second, a little bit less, but okay. And so they observe a transition between a flame around a fast flame, because the temperature, because the flow is very energetic, and because you have this increase by wrinkling, you transit, you know, between a flame with a jump, with a pressure decrease in the burn gas from few hundred meters per second to few thousand meters per second in a very short time, 10 minus 6 seconds. Once again, the Mach number of the lead shock that is observed in that case is typically 2.5, so that the temperature at the Neumann state is no more than 650 Kelvin, and this is well below the crossover temperature. So the transition was left unexplained. One of the key points to understand this transition is a study of my former students, PhD students, who developed a simple analysis of the following phenomena. He was considering the self-similar solution of a flame propagating at a given velocity behind a shock propagating at the velocity d, supersonic velocity. And in such a way that the distance between the two, the flame and the shock, increase like the time with the velocity, which is the difference of the two velocity, the flame, the shock velocity minus the flame velocity. And this is what we call, then more, in addition of that, they consider that the flame has a discontinuity, to simplify the analysis, whose velocity is the laminar flame's velocity relative to the burn gas, but multiplied by a wrinkling factor, considered as constant, and they look the solution of this problem for different value of the wrinkling factor. Right? This is the problem considered by Day and Joulin, let's say 35 years ago. It turns out that he noticed a very important point, But it turns out that this analysis was completely overlooked by the combustion community, as usual. When there is a top things occurring, like Zelovich and that, it took 20, 30 years before the combustion community. It's not a good sign of the combustion community, because they are not able to detect a main step, which is suggested by some people. Okay, this again is a representation of the problem by Joulin. There is another approximation he did, which is not, which is easily removed, but it's simple, which helps the calculation, is to assume that the shock is not strong, that everything is close to Mach equal 1. It's little bit high, but this it's not necessary. The results can be easily extended to the case where the Mach number is much larger than unity. But the analysis was performed in that case. Okay, here are the two main points of the analysis. Because it is a semi-permeable piston, the velocity of the gas here is because of the piston effect, simply relate to the burning rate times the wrinkling factor. Simple. Now, because they consider a steady state in between the flame and the shock, this velocity is also related to the propagation velocity of the shock by the Rankine-Hugoniot condition. And this Rankine-Hugoniot condition, you can transform that easily because the Neumann state has the same temperature, more precisely, the temperature in front of the flame is the same as the Neumann state. This is a basic assumption. You have a quasi-steady phenomena, self-similar. The problem is homogeneous here. This is a drastic simplification too. It works when everything is steady, when you do not have a strong increase, acceleration of the flame. Now it turns out that this is also related to the velocity is related to the temperature, and this is related to the temperature, the same, because the two temperatures are the same in front of the gas and beyond the shock. This is also because the unburned temperature is related to the burned temperature. You have a relation between the velocity and the temperature. Here you have a relation between the velocity and the laminar flame speed. And if you put together this results, you have this relation telling you that the laminar flame speed velocity should be proportional to the increase of the burn gas temperature with relative to a state which is called ici small zero, which is, for example, an initial state, whatever it is. But you know that according to the Zeldovich-Frank-Kamineski, the laminar flame speed is increased exponentially with the temperature of the burn gas. This is the main result of Zeldovich, of the thermal propagation theory of Zeldovich. Now, if you put together, if you enter this result in this equation here, you obtain this equation for the temperature of the burn gas, which is, you know, this is a temperature, you can consider that as an equation for the burn gas temperature here, and the parameter is a wrinkling factor which appears here, which is coming from the fact that the velocity is sub. Okay? So here. So you have an equation for the temperature, Tb, which is a transcendental equation again. Why? Because this is exponential on the right and linear on the left. All right? This equation can be put in this form. If you now introduce the reduced temperature, burn gas temperature, called X, capital X, and you introduce the parameter, capital K, as the folding degree S time a coefficient S, you obtain once again a turning point. And you see where is coming from this turning point. Once again, it's coming from the fact that the velocity, flame velocity, is a strongly exponential dependence of the burned gas temperature, Zeldovich. So now, what does that mean? Look at this result. On the horizontal axis, you have the temperature, which is the unknown of the equation. Good. On the vertical axis, you put the degree of folding, but you know, multiplied by this kappa is a parameter which is going to be for the unity. So this capital K here on the vertical axis is a measure of the folding. The horizontal axis, X, is a measure of the flame temperature. What do you see? Above a certain critical value of this folding factor, no more self-similar solution. Aha! Okay. So now this is, I have recalled the phenomenon here, you know. And the critical factor you obtain here is between when you put the number for flames, the activation energy, the gas expansion, the temperature, and so on, is close to 10. So for a critical, for a folding factor above a critical value, which is close to 10, there is no more self-similar solution. You are here, there is no more self-similar solution. So if there is no more self-similar solution, clearly there is unsteady solution, okay? But it turns out that I am going to show you the situation is worse. Not only there is no more self-similar solution, but you are going to have a solution that has a singularity in finite time. The flow is going to have a singularity in finite time. And this is one of my favorite results of the last of my life, scientific life. Before to be. Okay. So now what is very important, so this result, you know, the combustion community ignore completely Guy Joulin, but except one man, Grisha Sivashinsky, who was a student of Zeldovich, and we migrate in the 70s, something, 78, 79, in Western Europe. He was in Russia before. And he was interested in this result. In fact, even me, because at that time I was not interested in detonation. I was interested in flame. I did not see this result. And when I saw Grisha, he told me, you know, Guy Joulin will find out something really new that can explain the detonation. Okay, good. I said, okay, thank you to mention me because I was. And what he did, and he developed a lot of calculation since 2017, a lot of calculation, doing the following. He was taking a planar flame, good, ignite close to a wall, good, but he changed the kinetics, combustion kinetics. Just he changed the combustion kinetics. And he multiplied the reaction rate by a factor, you know, the square of the critical S obtained by Joulin. Why he did that? Because when you increase, you remember that the velocity is going like the square root of the reaction. So when you take the square, S, now you are simulating by such a simple experiment, numerics, you simulate the fact that the flame is going faster than the laminar flame because for Guy Joulin, it was because of the wrinkling. For him, it was because it increased the rate. The flame is still strongly markedly subsonic. So the nature of the problem is not changed. It is still a problem that is not easy to understand. And what did he found? He found that when you increase S, this S, there is no, he found the divergence of the flow of the flame velocity at finite time. Found that. He said. So I was very impressed by this result, even if it is not, the model of Grisha was not at all physical, because you cannot increase like that the reaction rate. The reaction rate is given by the collision of the molecule, and this is in the theory of Zeldovich. When you look at that, you cannot do that. But if you do that, this shows you that a singularity is going to appear in the solution. So now I try to have a better insight, physical insight into this problem. There is a main weakness in the analysis of Guy Joulin and Bruno Dehaye, versus the experiment is first that the shock is weak, but this is not a big deal. It's easy to reduce the calculation with a strong shock, and it works, like they predict. But the problem is that they are looking to self-similar solutions. And it is known from a long time by the experimentalists that the unsteadiness associated with an acceleration of the flame is an essential mechanism in the transition. So in the Joulin analysis, or in the Sivashinsky numerics, there is no such acceleration. You know, there is no such acceleration. So I was back now to the experiment. You know the science, even when you are pure theoretician, like I am, I did not. When I try to do experiment, I make the lab explode. So this occurred once in my life. I did not try to do any experiments again. You know, experiments in detonation are dangerous. So when you are a pure theoretician, you say you have to be back all the time to the careful experiments, to be driven in the right direction. Otherwise, you are a crazy theoretician. There are many crazy theoreticians. They are producing a lot of crazy analyses that nobody take into account. This is true, especially in theoretical physics. There are a number of crazy theoretical analyses that are nonsense. So science is not pure math. Science is experiments. Without experiments, there is no science. Okay? There is religion, there is what you like, philosophy, no science. Science, you have to be back to the experiments. So I went back to the experiment of Lieberman and Kuznetsov and Lieberman, in fact. And I developed recently with, in fact, two PhD students. I was not the advisor in charge, official advisor, because I am retired. You cannot be. So it's not my PhD, but I direct them. I help them. So Tofali and okay, forget about these young men. They are very good. And we did a theoretical analysis without assuming small heat release. Now, want to keep the real detonation. It is also, I want just to mention to you what I am doing now, inspired also by an experiment by Bikoff and other people recently. They observed DDT in long open tube. You see, what I am describing is what I am going to present also is a closed tube you ignite in a closed wall. Turns out that you observe DDT in experiments also. What is not clear, it is no. What now in that case the turbulence is going to play an important role. I will be back to that later. But I will not present this because the analysis is not ready. I am working on, and I have nothing clear to present for the moment. Now, let me tell you what are the basic mechanisms that you have to introduce in addition to all the mechanisms that I have presented. When you ignite a flame at the center of a closed end wall, close of a tube, an elongated flame is developing when it is laminar. An elongated flame is developing, and one of the main important phenomena is the following. This, when you look at this picture, you will understand immediately. It's raining? No. No. You see, this is an experiment developed in my lab long ago by, no, it is not Chloe, it's Clanet and Sirby in 96. They, something well known, that a laminar flame in a tube take the form of an elongated, a finger, they say, a finger-like flame. You see, this is the picture they use, and it turns out that the flame is in red here. But the essential phenomena that was understood by these people here to explain what it is called the tulip flame, but I will not discuss this phenomena, I will discuss another one, is that because of the burning rate in the lateral part of the flame, you see, this is the lateral part of the flame. You have a burned gas flow velocity going inside the axis of the tube. Now, because the tube is closed, when you inject flow like that, it cannot go back to the closed end because it is closed. So where it goes, on the other direction, back to the tip. So this is what I call a backflow. When you consider this part of the flame, the tip, the flame is pushed from behind by a flow coming from the combustion of the L's, lateral part. And this is an essential mechanism that I have introduced in my development. And the second important point is that they use, every time to have the detonation, they use very energetic mixture. To have detonation in the laminar, for laminar flame, for finger flame. Because I will explain to you later, there are other type of transition. But for this transition, this backflow is, to my opinion, the essential mechanism. It turns out that this backflow has been well documented recently, let's say 10 years ago, since 10 years ago. This is a group in France also, in Poitiers, where, you know, this is a flame. You see, this is a flame that has been ignite here. And now you see here the streamlines of burn gas. And you see clearly the backflow here that impinge the tip of the flame from behind. So what we are doing to develop first, what I developed first with Tofeli, student, PhD student. It's not my PhD, but he was PhD student of other people, and he was working with me with the permission of the other people on this problem for doing numerics, because I cannot do numerics by myself. I hate that. So he was doing the numerics, and he was so clever that he understood very well what to do. What the problem I consider is the following. I simplify drastically the problem. I say, I will focus my attention to the tip here. Why? Because in some analysis, not all, I will explain you later, the transition occurs somewhere there. So I focus my attention on this point. And I consider now, I forget about the curvature effect, I consider now the flame as planar. And that's problem. And there is no problem to justify that. I will give you the limitation. How can we quantify this approximation? And I consider so a semi-permeable piston to begin with burn gas flow from the flame is pushed from behind by a burn gas flow, but the essential part, the essential phenomena is that this burn gas flow is proportional to the length of the finger, flame finger. But this is one thing. But the other thing that it is proportional to the laminar burning velocity, because you have, it is like the wrinkle flame, you have the laminar burning velocity times the elongation here, okay? So this is a problem that we are looking at. This sigma here is the elongation. I will explain you that in detail here. you know, if you look, if you consider the conservation of mass, a model for that on this axis here, you have a source term on the axis which is coming from the flow, the radial flow of burned gas getting out from the lateral part. And if you look more carefully to what is going to be the profile of the longitudinal velocity of burned gas flow, it is this burned gas flow is going to be proportional when at this point at the tip on the burned gas side, proportional to the length divided by the radius and with a factor 2 because you are cylindrical. And you see now the flame velocity, that is a very important point, is this burned gas flow plus the laminar flame velocity in the burned gas, and this is because the burned gas flow is proportional to B, is proportional also the flame velocity to the burned gas velocity with a coefficient here which is similar to the wrinkling factor in the analysis of Joulin. Same thing. This is same thing. So let me finish this. Okay. Now, the important point in the following that I am going to develop in the next hour is that this flow, either the burned gas flow or the unburned gas flow, which is produced by the semi-piston effect of the flame, these are proportional to the laminar flame speed. At the temperature where you are, whereas at the temperature that you have here or here, but let's say mainly it's important to look to the temperatures that you have in front of the flame. So this problem now, in order to understand, is simple in a sense. It's not difficult to understand the model, but the model, essential part is that this flow, are all proportional, all of them proportional to the laminar flame speed, either burn, one burn, whatever it is, does not matter, and increase with the elongation. Longer is a finger, faster is this flame. But the key point is the temperature dependence, which is due to the laminar flame speed again. Okay, 10 minutes, 15 minutes breaks. I am right? Yes, this is the time. Yeah.